In this video, I'm going to talk about diffraction gratings. In addition to calculations using diffraction gratings, we're also going to talk about how to use it to distinguish whether or not I have one or two wavelengths when using emission spectrums. This is part of 9.3 and 9.4 of the IB Higher Level Physics Syllabus. It's not as relevant to SL students. Please read through the success criteria of what I plan to do in today's video. So first of all, with diffraction gratings, unlike with single slit or double slit interference that you may have already studied, with diffraction gratings, these lines are so close together we actually physically can't see them. The premise of it is just the same. I have light traveling from multiple different directions, and when they arrive here, they're going to have to be in phase for constructive interference to happen. That's going to occur because I've got different path lengths coming from each of these slits. Now, when I'm talking about slits, I'm talking about, you can see here, we have 1,000 lines per millimeter, and that's why I'm saying we actually can't see them. In this case, we will have a central maximum, the one in the middle, straightforward, and we start counting above and below from there. So I have here some pictures of a laser and the light actually going through the diffraction grating. Now, one of the things I want to point out about this pattern, yes, you can see it does look a little brighter straight through, but look at how much empty space there is between our actual orders. Because of this, we cannot use the small angle approximations when we have diffraction gratings. It actually stands out in your data booklet because it's the only one that still has sine theta in it. Let's point out a few more differences between single, double, slit diffraction and diffraction gratings. These diagrams come from Hyperphysics through the Georgia State University website. So first of all, we've got the single slit, and we had this big, large central maxima, twice as wide as the others, and we had a fairly wide central slit. Then we had double slit diffraction, and now we've got more narrow slits, and if this value of B was large in comparison to little d, which is the distance between them, we also had this single slit modulation. You might want to watch my other videos if that's unfamiliar to you. Now, when we get to diffraction grating, we have so many of these different slits here. We can't see them, but not only that, we have to be pretty precise for them to actually add up and get a place of constructive interference. So notice that the width of these maxima are basically just lines in comparison to edges where we had a bright center, and you could see that would gradually decrease. We used to call them fringes. Here in diffraction gratings, we typically call them dots because they are very bright or not. You can see the very small amounts here, but typically bright or not. So here's our diffraction grating equation, and you can get this by looking at, as I said, the constructive interference that's going to have to happen. It will need to be a multiple of lambda in order for us to keep our waves in phase. It has d sine theta, and sine theta has to be there because we can no longer use the single slit, the small angle approximations. So d has to be the distance between our slits. But in my picture before, I said I had 1,000 lines per millimeter. That's not the distance between the slits. If I want that, I'm actually going to need to have 1 over 1,000 lines, notice per millimeter. Now, if I use our fractions, you invert and multiply, this will become decimal 001, and it will be millimeters between my slits. One other thing I'll point out here is that value of n. So as I said, if here's my screen, we are going to have a very bright one in the middle, that's n equals 0, and then this dot over here we're going to call n equals 1, and over here this is also first order, n equals 1, and we number them from the center. Okay, so a narrow beam of monochromatic light of wavelength 590 nanometers is directed normally at the diffraction grating. All of our examples in IB will be directed normally to the diffraction gratings. The spacing of the diffraction grating is 1.67 times 10 to the minus 6. Oh, so we got lucky here. We already have little d. And we want the angle of diffraction for the second order of the diffraction beam. So in this case, n will equal 2. We're looking for theta. So let's start with our equation. I'll rearrange for theta. Don't forget, if you want your answer in degrees, then you better have your calculator in degrees. Especially in this unit where you flip back and forth between radians and degrees. I have mine in degrees. And I get 45 degrees. Now part B says, show that no beams higher than the second order can be observed at this wavelength. Well, if you think about it, the maximum value of theta is going to be 90 degrees. We cannot have it being diffracted any greater than that. So what we need to do then is we need to go and calculate what our value of n would be if we're going to use this maximum value of theta. Now we also know that sine theta, in this case sine 90, is going to equal 1. So if I rearrange, I'm going to get 2.8. Now in this case, I cannot round that up to 3 because we already are at our maximum of 90 degrees. So in this case, we have a maximum order of 2. Another thing that usually gets asked in these kind of questions would be, what is the maximum number of dots? So don't forget, we would have the center dot, n equals 0, and then 2, n equals 1, and 2 of n equals 2, giving a total of 5 dots. Now, diffraction gratings are used a lot when we look at light given off from emission spectrums. So, for example, I have down below here from sodium lamps. Sodium lamps are traditionally used a lot for developing film because usually you would only see the sodium color, the yellow lights. And the whole point about this is that actually one light, one wavelength, or is it bright because there's 2 lines there? And so we need to think about what kind of diffraction grating we're using to be able to tell the difference. Now, if you haven't seen my video on single slit resolution, I talk about the Rayleigh criterion there in more detail. You may want to check that out. He says that if we have 2 sources and they are resolved, then they are going to be far enough apart so I can see the 2 peaks. When we have just resolved, that means the peak of one of them is going to be over top of the minimum of the other, and similarly here. Anything closer than that, and it's going to be unresolved. So the point here is, with diffraction gratings, what kind of angle am I going to need, or at a certain angle, can I get our 2 lines to be far enough apart that we can have them as being just resolved? Now, in order to do this with diffraction gratings, you can see here that I've got the equation from our data booklet. Resolving power is lambda over delta lambda times m and n. Well, let's look at the first part here. First of all, it doesn't tell us which wavelength to use. We've got 2 different wavelengths, and so I really wish this was the case, but it really should say average. And in some places they might use a slightly different approach, but this one will be completely acceptable for the IB program. So on the top, use the average of the 2 wavelengths, and then on the bottom, use the difference between them. That will give us the resolving power that's needed. Now in this case, it's not talking about the resolving power for a particular set of doublets or particular wavelengths. What we're looking for here is based on the actual number of lines per millimeter. M stands for the order that we're looking for. I know in the previous slides I've always used it as little n, but for some reason we use little m in this case. And capital N stands for the number of lines we're actually using. Just because in this case it says that we have 2,500 lines per millimeter, that doesn't mean that the entire diffraction grating is being used with the light landing on it. In this case, it says there's actually only 5 millimeters, or 5 times 10 to the power minus 3 of a width of the light that's landing on this diffraction grating. So first of all, let's think of the number of lines that are actually being used. So I have a width of 5 millimeters, and I have a possibility of 2,500 lines per millimeter. So I'm actually going to be using then 12,500 lines of my diffraction grating. Since I'm interested in the second order lines, that means my total resolving power is going to be 25,000. So depending on which kind of wavelengths I was using and the differences between them, I could end up having values anywhere in here. As long as the resolving power is going to be at least this much, I will be able to see 2 distinct lines. So here's a slightly different question. In this case, I have 2 lines at 589 and 589.6 for those 2 sodium lines I was talking about earlier. It says, what's the minimum number of lines per millimeter I need if my diffraction grating is being used at the first order spectrum, and we're going to assume our beam of light is 2.5 millimeters wide. So let's start by writing the equation. And we'll substitute in our known values. Remember, this value on top is the average. So 589.0, 589.6. Our average there is 589.3, with the difference being 0.6. Now, these are both in nanometers, and we will cancel out the nanometers. So I can be a little lazy here and not write that part in. I want my first order, and I'm looking for the total number of lines that we're going to use. And in this case, I've got 582.16 according to my calculator. Now that's just the total number of lines, but the question asks what the minimum number of lines per millimeter are. So I'm going to need to take that value. I'm going to divide by the number of millimeters I'm actually having in my laser beam, and it is asking for lines per millimeter, so it is appropriate for me to leave this value in millimeters. And now I'm going to get 392.8. Now let's think about whether or not I should round this number. I'm looking for the minimum number of lines per millimeter, and when I have this, think to yourself, will 392 be appropriate? Would that be enough lines? And the answer is no. So in this case, it needs to be actually 393. I must round up in this case in order to have enough lines that are going to allow me to actually resolve these. And so let's take a moment again to read the success criteria that you should be able to follow now that you've watched this video. I hope that's helped.